This is experiment tip A concept for DT1 and DT10. We are going to present you the sizing, costing, and mechanical design of heat exchanger. So first, I'm going to talk about the heat exchanger design. In heat exchanger design, the equipment sizing is important for us. So before calculating the capital cost based on process equipment, the process engineer must carry out a preliminary sizing of the equipment. Although each process will have some unique pieces of equipment, there are some general categories applicable to most designs. Next is the heat transfer media. Heat transfer media are classified as coolants and heat sources. Coolants are when heat is transferred to them from process streams, and heat sources are when heat is transferred from them to process stream. So we can refer to table 12.1, which is the heat transfer media of different medium such as coolants, heat sources, and the typical range for the temperature and the mode such as vaporizing, sensible, and condensing. For the temperature driving force for heat transfer, E is the smallest difference between the temperature at two ends. It sometimes occurs at an intermediate location if phase changes occur, for example, vaporization and condensation. It can cause temperature crossover within the exchanger, thus violate the second law of thermodynamics. Selection of the appropriate change of the minimum temperatures is important to avoid temperature crossover, especially when the phase changes. According to heuristic 26, near optimal minimum temperature approaches in heat exchangers depend on temperature level as follows: 10 Fahrenheit or less for temperatures below ambient, 30 Fahrenheit for temperatures at or above ambient up to 300 Fahrenheit, 50 Fahrenheit for high temperature, and finally 250 to 350 Fahrenheit in the furnace for flue gas temperature above inlet process fluid temperature. Furthermore, pressure drop is one of the important components in heat exchanger design. For process design when using a simulation program, pressure drops due to friction can be estimated by referring to heuristic 31. An additional pressure change happens if the heat exchanger is placed vertical due to pressure head and potential energy. Based on heuristic 31, estimate heat exchanger pressure drops as follows: 1.5 psi for boiling and condensing, 3 psi for gas, 5 psi for low viscosity liquid, 7 to 9 psi for high viscosity liquid, and finally 20 psi for process fluid passing through a furnace. The table beside shows the pressure drop based on the liquid stream, vapor stream, condensing stream, boiling stream, and process stream passing through a furnace.
Now I'll be explaining on the heat exchanger, where it is a device which transfers heat from one medium to another. It is used in many engineering applications such as refrigeration, heating and air conditioning systems, power plants, chemical processing systems, food processing systems, automobile radiators, and waste heat recovery units. As shown in the slides, there is a variety of standard sized equipment is available for heat exchange, which are double pipe heat exchangers, shell and tube heat exchangers, air-cooled fin fan heat exchanger, and compact heat exchanger. I'll be explaining on the double pipe heat exchanger. It consists of an inner straight pipe with circular cross-section, concentric tube, and supported within an outer straight pipe. The hot and cold fluid are fed into the heat exchanger in counter-current flow. Also, the heat transfer area is based on the outside wall. The stream with high temperature or pressure or corrosive passes through the inner pipe. Longitudinal fins can be added to the outer surface of the inner part of the inner wall if there is gas drip. For shell and tube heat exchanger, it has a higher heat transfer area per volume due to the large number of small tubes in a shell. Tubular Exchanger Manufacturers Association (TEMA) provides standard for shell and tube heat exchanger designation. When making preliminary calculation or employing shell and tube heat exchanger, there are useful heuristics that can be applied, which is heuristic 54 and heuristic 55. For shell and tube heat exchangers, tubes are typically 3/4 inch outer diameter, 16 feet long, and on 1 inch triangular spacing. A shell of 1 feet diameter accommodates 100 feet square, 2 feet 400 feet square, and 3 feet 1100 feet square. Next, the tube site is for corrosive, falling, scaling, hazardous, high temperature, high pressure, and more expensive fluids. The shell site is for more viscous, cleaner, lower flow rate, evaporating and condensing fluids. Now we will be moving on to the air-cooled heat exchangers. It is a good option when the cooling water is in short supply. The peripheral fins on the outside tubes increases the outside heat transfer area. The design is depending on the entering air temperature, where if the inlet air is at 30 degrees Celsius, the outlet temperature will be 60 degrees Celsius. If the inlet air is at 20 degrees Celsius, the outlet temperature will be 50 degrees Celsius. The heuristic for an air-cooled exchanger is the tubes are typically 0.75 to 1 inch in outside diameter. The ratio of fin surface area to the tube outside bare area is large at 15 to 20. Fan power requirement is in the range of 2 to 5 horsepower per million British thermal unit per hour transferred, or about 20 horsepower per 1000 feet square of tube outside bare surface fin field area. Minimum approach temperature is about 50 degrees Fahrenheit, which is much higher than with water-cooled exchangers. Without the fins, overall heat transfer coefficients would be about 10 British thermal unit per hour feet square degree Fahrenheit. With the fins, overall heat transfer coefficient is equals to 80 to 100 British thermal unit per hour feet square degree Fahrenheit based on the tube outside bare surface area. The next heat exchanger type is compact heat exchangers. It is slowly replaced by shell and tube heat exchanger due to the TEMA standards. It can be divided into 3 parts, which are plate and frame, spiral plate, and plate fin heat exchanger. The compact heat exchanger is easy to be cleaned, has high heat transfer coefficient due to the corrugation plate design. It is strongly recommended for sanitation services. However, the operating temperature and pressure is at 400 degrees Fahrenheit and 300 pounds per square inch gauge, respectively due to the gasket seals. Also, it is suitable for no-phase change heating and cooling process as well as viscous and corrosive fluid. The simplest expression for the mean temperature driving forces is determined when the following assumption hold. First, stream flows are at steady state. Next, stream flows are countercurrent or co-current to each other. The overall heat transfer coefficient is constant throughout the exchanger. Each stream undergoes only sensible enthalpy changes, heating or cooling with constant specific heat. Heat losses are negligible. Thus, the equation 12.2 can be used if the flow directions are combinations of countercurrent and co-current in multiple shell and tube passes. To calculate the true mean temperature driving force, the correction factor can be calculated by using the equation 12.4. Since the values are approximate, the basis for the area is of no concern. Typical estimates of heat transfer coefficient for shell and tube heat exchangers are given in Table 12.5. The values include a falling factor contribution referred to as total dirt equal to RF outer wall plus RF inner wall. The steps in typical design procedure are define duty heat transfer rate, fluid flow rate, and temperature. Next, collect the physical properties of the fluids. Design the type of heat exchanger to be used. Select trial value for the overall coefficient. Calculate the mean temperature difference. Calculate the area required. Decide the heat exchanger layout. Calculate individual coefficient. And calculate the overall coefficient. Compare with trial value, step 4. If the value differs significantly, return to step 6. Next, calculate the heat exchanger pressure drop. If unsatisfactory, return to step 7 or 4 or 3.
Now we try to do one exercise. The question is, design a shell and tube heat exchanger to cool 60,000 pounds per hour of 42 degree API kerosene from 400 to 225 degree Fahrenheit by heating 35 degree API distillate from 100 to 200 degree Fahrenheit under the following specification. Neglect the tube wall resistance. Use 3/4 inch 60 BWG tubing outlet diameter equal to 0.75 inch and inlet diameter equal to 0.62 inch. Use 1 inch square pitch and place kerosene on the shell side. The summarized information given are degree for shell and tube side fluid, heat capacity for both inlet and outlet, flow rate, velocity, temperature hot and cool, and specific gravity for shell and tube side. According to heuristic 54, for shell and tube heat exchanger, tubes are typically 0.75 in outlet diameter, 20 feet long, and on 1 inch triangular spacing. Now for calculation, step 1 is to calculate heat duty by using formula Q equal to mCp delta T, and we get 6457500 BTU per hour. Step 2 is to calculate the required mass flow rate of API distillate using formula mass flow rate inlet equal to Q over Cp inlet delta T. And we get 129,150 pounds per hour. In step 3, we estimate the overall heat transfer coefficient. The figure here shows table 12.5 of overall heat transfer coefficient for shell and tube heat exchanger. The value of heat transfer coefficient for kerosene is 40 BTU per hour feet square Fahrenheit. For step 4, we calculate log mean temperature R, S, and Ft value. For log mean temperature, we need to find value of delta Ty and delta T2 and insert it into the formula, and we get the value of 159.6 degree Fahrenheit. For R value is 1.75 and S value is 0.33. For Ft value, we insert R and S value into the formula and we get 0.87. In step 5, we calculate heat transfer area by using formula of heat flow rate and we get 1168.54 foot square. Since the heat transfer area is larger than 200 feet square, therefore a floating head shell and tube heat exchanger is chosen. In step 6, we calculate total cross-section area per pass and total cross-section area per tube by using formula, and we get 0.1407 square for total cross-section area per pass and 0.0021 foot square for total cross-section area per tube. For step 7, we need to calculate number of tubes per pass (T) by dividing value of total cross-section area per pass with the total cross-section area per tube, and we get 67.13 tubes. Our estimation is 68 tubes per pass. In step 8, we need to calculate heat transfer area per tube, AT, and number of tube passes, NP. We insert all the value into the formula and we get 3.25 feet square per tube for heat transfer area per tube and 6 passes for number of tube passes. Last step is to select shell's diameter ds. From table 12.6, we assume shell's diameter ds is a 32-inch will hold 408 tubes on square pitch in a 6-pass exchanger.
By using the same example, I would like to introduce the Excel tool for the heat exchanger sizing calculation. Basically, to use it, you just need to insert all the given values of the shell and tube heat exchanger information. Next, we also need to insert the overall heat transfer coefficient based on the shell side and tube side media.
The values of number of tube passes and heat transfer area per tube are calculated automatically since all the equations are linked to each other.
Next, we move to how to purchase cost for heat exchanger. So for the shell and tube heat exchanger, usually the most important data that is needed to purchase cost is surface area. The equation 16.43 needs to be used to calculate the free onboard FOB purchase cost for shell and tube heat exchanger, and this is the formula for the purchase cost for shell tube heat exchanger, where the FP is the pressure factor, FM is the material factor, FL is tube length factor, and CB is correlation factor. So this is the figure 16.10, which is the base FOB purchase cost for shell and tube heat exchanger for floating head, fixed head, U-tube, and kettle riser. And this figure for the carbon steel and pressure to 100 psi gauge and for 20 feet long tubes. So to find the purchase cost, so we need to know the size factor first. They range from 150 to 12,000 feet squared, and then we can find the purchase cost for the heat exchanger. And then this is the formula to find the correlation factor CB for the floating head heat exchanger and fixed tube sheet heat exchanger. Then this is for U-tube heat exchanger and also for the kettle type heat exchanger. This is the formula given for the pressure factor SP, and P is based on shell side pressure in PSI gauge and applicable in ranging from 100 to 2000 PSI gauge. Next is tube length correction FL, and this is the tabulated data to find the FL. For the material factor FM, this is the formula to calculate where A is the area in square feet. So we need to know the materials of construction shell or tube, and we can know the A and B to put it in the formula to get the material factor. Then we move to the double pipe heat exchanger, whereas the area should be less than 200 square feet, and the equation had been used to calculate the free onboard purchase cost for shell and tube heat exchanger CP. And this is the figure for base FOB purchase cost for double pipe heat exchanger, and the formula for correlation factor is CB equal to exponent 7.2718 plus 0.16 ln A. And this is the formula to calculate the pressure factor that ranging from 600 to 3000 psi gauge, and material factor, which is FM equal to 2.0 when outer pipe is carbon steel and inner pipe is stainless steel, and FM is equal to 3.8 when both outer and inner pipe is stainless steel. So this is the fire heater that is used to heat or vaporize non-reacting process streams at elevated temperatures beyond where steam is normally employed. And then the heat duty range from 10 to 340 million BTU per hour. And then the fire heaters are complete package unit with standard horizontal tube of carbon steel, adequate for temperature to 1100 Fahrenheit and pressure to 500 psi gauge. And then for the base cost depend on heat duty absorbed by process stream. And this is the formula for pressure factor and material factor for fire heater. This is the figure for base FOB purchase cost for indirect gas fire heaters of the box type. And it is the other specific purpose for fire heater that we can see for reformer, pyrolysis, hot water, and so on.
So we move on to exercise 16.1. In examples 6.1, 6.5, and 6.7, a toluene hydroalkylation process is synthesized. Material and energy balance calculations on the process give a combined feed to the hydroalkylation reactor of 5,802 IBmol per hour, containing mainly 35 value percent hydrogen, 58 value percent methane, and 7 value percent toluene at 127.6 degree Fahrenheit and 569 Celsius. The stream is heated to 1000 degree Fahrenheit in a heat exchanger by 6010 IBmol per hour of quenched reactor effluent, which also contains a significant percentage of hydrogen, entering the exchanger at 1150 degree Fahrenheit and 494 Celsius, and existing at 364.2 degree Fahrenheit and 400 89 The calculated heat duty Q is 69,360,000 BTU per hour. Estimate the area of the heat exchanger and the FOB purchase cost at CE index of 600. The information given are combined feed enters heat exchanger with 93.1% molar vapor fraction, combined feed exits heat exchanger as superheated vapor, quench effluent enters and exits as superheated vapor, vaporization occurs on the combined feed side, zone analysis yields mean temperature driving force, delta Tm of 190.4 degree Fahrenheit, and driving forces 150 degree Fahrenheit and 236.6 degree Fahrenheit. Assuming overall heat transfer coefficient U of 50 BTU per hour feet degree Fahrenheit, and the last one is heat duty Q equal to 69,360,000 BTU per hour. To calculate heat transfer area, A equal to Q divided by U multiplied with delta Tm. The answer is 7,290 square feet. The specification of heat exchanger, since the heat transfer area is larger than 200 square feet, therefore a floating heat shell and tube heat exchanger with 20 feet long tubes is chosen. Pressures on both the shell and tube sides are in the range of 500 to 600 psig. Select a design pressure of 700 psig. Because temperatures are high as 1000 to 1150 degree Fahrenheit, carbon steel cannot be used as the material of construction for either the shell or tubes. Because the hydrogen content of both streams is significant, CRMO alloy steel, which is often used in the temperature range of this exchanger, is not suitable either, and stainless steel must be selected. As you can see, the picture is floating heat exchanger. The corrosion factor can calculate by using the formula, and the answer for CB is $120,100. To calculate material factor, we need to refer table 16.25 material of contraction factor FM for shell and tube heat exchanger. Since the stainless steel selected, the value for A and B must be referred in the table, and the answer for FM is 4.05. The pressure factor FP can calculate by using the formula, and the answer for FP is 1.19. Meanwhile, for FOB purchase cost at CE 600, it also can calculate by using the formula, and the answer is $630,000. There are a few.
For the heat exchanger costing Excel tool, we are using the shell and tube heat exchanger as the example as well. So we need to insert all the known values, and to calculate the cost, we need to calculate the pressure factor, material factor, tube length correction, and correlation value. Insert the A and B value and tube length correction value by referring to the tables provided. The correlation equation differs for different types of heat exchanger. Thus, you may utilize the equation stated based on the desired situation. You may also use the Excel tools in Sheet 3 and Sheet 4 to conduct the costing calculation for double pipe heat exchanger and fired heater.
There are a few parts of mechanical design for heat exchanger, which are shell, baffle 2, tube, heat cover, and the last one is shell cover. Next, this is heat exchanger specification sheet. How to use this specification sheet? There are 3 parts which are details for customer, performance of one unit, and construction of one shell. For performance of one unit, we need to know the basic information and operating conditions for the chosen heat exchanger, such as temperature in and out, inlet pressure for shell and tube, and others. Then, for the construction of one shell, the main is design features. We need to know the design sizing for the chosen heat exchanger. The physical dimensions also important since we must provide number of tubes, tube length and pitch. There are more information that we need to write in the specification sheet.
That's all from DT1 and DT10. Thank you.